Okay, so last time we were together on Tuesday, we worked this problem. I just kind of want you to review a second and think that if my applied load is a constant load, all right, then remember as you're really doing integration as you go down the line. So when you integrate a constant, you get a linear function, first order, and when you integrate that, you get a second order. Okay? So now think over here. This one is already first order. So when you integrate that, you're going to get second order, and then you're going to get third order. Can you foresee that might be an issue with their technique? It's easy to find the area under a triangle, first order curve, right? That's going to produce a quadratic, a parabolic, second order. Anybody happen to know the area under a general quadratic equation? I do, but only in one case, and it doesn't always happen. So you can see that this is one that we're going to try to do, but it'll probably be a weakness of this method. You guys are really good at finding areas of rectangles and triangles, but not so good with areas of parabolas. So it gets a little tricky. So this is where the method does break down. Now, obviously, if you look at this thing, can you write this as a function of x across the whole structure? Yeah, so it'd be really not hard to actually integrate that function and get a shear equation, integrate the shear equation, and actually get a moment equation, and then graph it. So you're going to have these kind of tools at your disposal, and you should be able to kind of observe the loading and decide, which one should I use? So as we move towards the exam, I may not tell you which one to use. I may just say, I want to know what the moment at some point is. Or I want to know the variation of the moment between this length. I won't tell you to draw a diagram, or I won't tell you to write an equation. I'll let you decide which way you want. Engineering, decisions, thinking.
When you say variation of moment between these points, what do you mean? Like the entire range that the
could
moment
be.
could span?
Well, it'd be, okay, what's the variation of the moment between 0 and L look like? You could write an equation, you could draw a diagram. Those would communicate that. And then I might ask you, what's the maximum?
Okay.
You could pick that off of your diagram. You could probably pick it off of your equation. Sometimes the graphical technique will be the best way. Sometimes it will not. Now, and you already know that if the load is discontinuous, you're going to have to write a bunch of equations, right? When we looking at discontinuous loads, when we draw the diagram form, it may be pretty easy to do. So keep that in mind as we work through these. Okay, so with all that said, let's see if we can work that problem and see where we have some issues. So again, I will tell you that the reaction on the left side will be W naught L over 2, which is just the area of the curve. And the resultant moment there will be W naught L squared over 3. And that's just this concentrated equivalent force, which is W naught L squared 2 times 2L. 2L over 3. That's how I get that. So with that given, now I can start through. Now remember the process that I like you to follow, and I think is a good one, is to take the known values you have and put them on the graph and see where you should go. So starting on the left side, I look up, what's my shear on the left side? It's this value, W naught L over 2, is it positive or negative shear? Is it trying to make this rotate clockwise or counterclockwise? Clockwise, so that is positive. So I'm going to start off at a positive value of W naught L over 2. Now we know that the change in shear is the area of the load curve. So what's the change in shear over the whole length? What's just the area of this triangle? 1/2 base L times height W naught. And that force is negative or positive? It's down, so it's negative. So if you start at WL over 2 positive and then you subtract this change, you get 0. Does it make sense that there'd be zero shear at this free end? Yes. So now you come back and you say, okay, what's the slope of the shear diagram? Well, it's given by the value of the load. What is the value of the load at x equals 0? It is 0. So I'm going to start off with a 0 slope. And then the slope gets progressively larger until it gets to the W0 value. And what is that value? Positive or negative? Negative. So if I actually drew it over here, you would actually see that this slope is negative W0 to 1. It's a negative slope. So now I get to draw a curve that fits through that. What's that?
You get the swag a curve.
I get the swag a curve?
Just ask Dr. Meyer about it.
Oh, I was gonna ask you if I just said something inappropriate.
Yeah.
You know, you kids today, I can't keep up with you. What is that? A parabola. Yeah, a parabola. Now, is it? It's a parabola. Now, here's an interesting thing about this particular parabola. It starts off with a 0 slope and ends in something. This is actually called a parabolic section, and it's easy to find the area of this. In fact, if you look up in the back of your book, let's see if I can find it for you. Right there, you will see a semi-parabolic section. So one end is going to be flat, and the area of that is 2/3 base times height. That's easy to remember. And of course, the little piece that would be here that would make it a rectangle is called a spandrel, and it's 1/3 of that. So if you add the spandrel and the parabola sections together, you get a rectangle base times height. So those are cool. You can remember those. The problem is when it's not a parabolic section. It's just a part of a curve. Then there's just no way to do it with this graph. And really, I don't expect you to remember these. The only reason I do is I've been doing this since 1993, and I kind of remember it. So, at this point, you would think, I don't remember the area of a parabola. Oh, that's really big. Right? So this is where the graphical method kind of breaks down. But I just happen to remember that. So I'm going to see if I can remember that this area is what? 2/3 base times height, right?
Yeah.
And what is 2/3 of the base times the height? That will be the change in moment is the area of this curve. This moment, this is a positive area. And my moment's going to start initially here at what value?
V0 L squared over 3.
Is that a positive bending moment or a negative bending moment? Is it going to make you frown or is it going to make you smile? Frown. So you're going to start off negative. That'll be minus W0 L squared over 3. And what's the area of this? 2/3 base L height this. And if you calculate that, that's positive W0 L squared over 3. So you start off with negative, you add this to it, you get to 0. Does it make sense that you have 0 bending moment at the free end? Yes. Now, what's the shape of this curve? Remember, the slope of the moment diagram is given by the shear. So let's start here. What's the shear value? It's positive. So I'm going to start off at a positive slope. And I'm going to decrease to a value of 0. So I will now fit my idea of a cubic curve through those bits. And there it is. So I was able to pull that one off, but that's the rare case where you'll know the actual area under a parabolic section. One that's actually a parabola. One that actually has a 0 slope either at one end or the other. That may not be the case every time. Okay. Questions about that? We're going to work a bunch more of these. All right.
When you assumed those moments at the fixed points, why did you not use the sign convention?
I did.
Well,
I didn't solve for them. I just knew what they were because I
Okay.
did them in my head real quick.
Gotcha.
And that's the
I
resultant
can see
moment.
that. Yeah, it'd be
And that one's negative.
Gotcha.
If I were to do this, which I'll do in some other ones where I don't know these off the top of my head, I would assume a positive moment there and write my statics equations, and I'd probably, in this case, get a negative value.
Can you assume the slope at the shear diagram was negative because the arrows were pointing down on the load?
Well, remember the slope of the shear diagram is given by the load. So if you go up and look at the load, it starts off at 0, and it increases to a large value, but remember our load is down, and down is negative. So that's why I have a negative slope at the end.
Thank you, sir.
Okay, cool.